So therefore, this is the second class of gravitation, I suppose. Now, a very clear point is that already electrostatics is done, and you know the formulas for variation of electric field due to different distributions as a function of R. And you know, in case of volume charge distribution, in case of volume charge distribution, you know, at any point inside which is at a distance r, the intensity of gravitational field E is given as formula 4 by 3 pi g rho r. Remember, this is always attractive, you know. Right. Now, I require this concept to discuss a new concept called pressure, gravitational pressure. So, due to the self pull towards the center, what will happen is a point at some depth d and some other depth 2d will experience a different forces. Pressure is what we will call. Now, that is the point which right now I am going to highlight. For example, you take gravitational pressure. This is the heading. Now you imagine a sphere. E-lights. Imagine a sphere. Now what is happening in this sphere? Try to please understand. Here is some point. And this point is assumed to be on the surface of an elemental shell of radius r. Now I am assuming a very small element over here. You can see that element. What is the significance of this element? This element will have mass dm, okay, width dr. So therefore mass can be written as rho dr some delta A. Delta A is the area. Width, thickness R along the radius dr. Rho, mass per unit volume. Right. That is the mass. And at this point, can you please help me in writing intensity of gravitational field? Otherwise, I am not convinced. I am not convinced. What I believe is at this point, you may have pressure P minus dP. At this point, I will have a pressure P. Actually, as you go down, pressure increases. As you go down, pressure increases. That is the pressure above and below. Now, what is the force, inward force? Inward force experienced by the element. This is nothing but difference of pressure dP, very good, into area, which is nothing but E times dm. Agreed? Everyone in this class, just please confirm whether you agreed it or not. Done? Any doubt? Now, if you are compromising, I cannot explain anything. If you are clear, we will proceed further. Everyone in this class. Palvita, clear? Right. Now, what is going to happen? I know E. Just now I have given 4 by 3 pi g rho r. This is what we will call intensity of gravitational field at that point. Of course, directed towards the center. So therefore, from 1 and 2, I will have dP into delta A is minus, don't confuse why I'm writing minus, I'll explain. 4 by 3 pi g rho r into rho dr delta E. So cancel this. dP is minus 4 by 3 pi g rho r square r dr. Hold on. Why there is a minus sign? That you need to understand now. It's attractive. Minus sign indicates attraction in nature towards the center. Now you do the proper integration. So I am taking some R. At that point, say the pressure is P. Can someone please help me? When I put capital R on the surface, is there anyone exerting force on my top towards the center? No, we are considering zero atmosphere. No, that is not considered as gravitational pull. Gravitation based. No. So on the surface, we almost consider as zero gravitational pull. Right. Right. So therefore, zero. But very simple. What is pressure? I will explain. Suppose I caught an excellent catch. Then what will happen in a very sensitive moment, very pressurized condition of the match? Every player will get excited and fall on me. Now, one person, I'll feel some pressure. 2 persons, 3 persons, 10 persons, all full player, including wicketkeeper, leaving both the umpires. So what will happen? I will feel immense pressure. Now, imagine the topmost person. Will he feel any pressure? No, you won't feel any pressure. The pitiest part is the person who caught the catch. So therefore, he will feel extreme pressure. So the one who is at the center feels extreme pressure conditions. Therefore, from this I can say P is 2 by 3 pi g rho square capital R square minus small r square. Remember, this is a very important formula at a later stage. If you have any doubt, any level, ask me. I'll post these notes immediately after the class. Right. Someone please take, Nana, you just take care. You leave the class only at the moment when I post this in the group. So this is the concept. This concept is called gravitational pressure. Any doubt? So very clear. The gravitational pressure, you can comment like this. On the surface, almost zero. At the center, extreme pressure conditions. Right. So I'll move further. the next concept. Okay. Relation between small g and capital G. One is acceleration due to gravity. Remember, you should use acceleration due to gravity only for Earth. Reserved. The moon is a word which is supposed to be used for our moon. Got the point? So when I am using gravity, it usually refers to Earth. Otherwise, planets' acceleration due to gravity is what they will use. Right. Now, you take a situation like this. This is a Earth, for example. Earth can be considered as a uniformly, actually this is wrong, but right now you consider it's a uniformly mass distributed planet. And on this, you just placed an object. You just placed an object like this. Now, this object will experience gravitational force as per Newton's universal law of gravitation. What is that gravitational force? G into capital M into small m by r square. Right. You know, this force you will experience as the normal reaction force or the pressing force at that point, which you will usually call that as the weight force, mg. Equation 1, equation 2. Right. So this element will experience a force according to Newton's universal law of gravitation. And for the equilibrium of object, normal force and Fg should balance. So therefore, we can write mg is G capital M small m by r square. Therefore, small g is G capital M by r square. So this is the relationship between acceleration due to gravity and universal gravitational constant. Okay. So from this relation, we can actually observe that the acceleration due to gravity is nothing but the intensity of gravitational field at that point. I remember G is nothing but intensity of gravitational due to Earth. Right. And not only that, another important observation is, please see, I put small mass, independent of the shape. So this is independent of mass, shape, size, etc. of the object. So even this is what we will call as acceleration due to gravity. This we will call as acceleration due to gravity. And remember, used only for Earth. This term is used for earth only. Right. Now, on the basis of this, we will discuss on different other cases. First, variation of G. Variation of G with altitude, height. Now you consider a situation like this. I am considering Earth as a sphere. Now you have a point A over here, another point B over here. And this distance is R. So clearly OA is R. OB is R plus H. Now Z at A is defined clearly as GM by R square. G at B, GM by R plus H whole square. Okay. So therefore, GB by, now this we will normally represent as G naught. Normally. So GB by Z naught is nothing but R square by R plus H whole square. So with the height, Z decreases. So GB is Z naught times R by R plus H whole square. See, there is a special case in this. Remember, this is a special case. For H much lesser than R. So therefore, this you can write it as GB is G naught times, you can write it as 1 plus H by R whole to the power of minus 2. And this will become, according to binomial expansion, this will become 1 minus 2H by R, according to binomial expansion. Right. So therefore, with altitude, definitely G decreases. And you need to use this formula only for H very small when compared to R. Any doubt in this, feel free to question me. Every student in this class. Right? Sure? Next. Sure. అర్థమవుతుందా మహంత్? Right. Next. Now we will study variation of Z with depth. Today I'll cover theory part totally. If time permits, I'll discuss some numericals. Otherwise, again afternoon, I'll take one more class to continue this, to cover this. Variation of G with depth. Right. See, try to please see that this is Earth. Right. Now you are at some point which is at a depth D. Now let me imagine right? Now this is your Earth, and this is R, and this is some distance small r. Clearly, small r is r minus t. Just now we have studied, at this point, uh, G, intensity of gravitational field, is nothing but 4 pi 3 pi G rho small r. So therefore, so you take a point here, for example, now this is point B and this is point A, for example. Then what will happen? At the depth GD, we will write this as 4 pi 3 pi G rho capital R minus T. So on the surface, you will write as simply 4 by 3 pi G rho capital R. Equation 1, equation 2. Equation 1 by equation 2 is GD by G naught is equal to R minus D by capital R. Okay. So which clearly implies G naught into 1 minus D by R. Array, with the height, with the altitude, G decreases. With the depth, G decreases. And one more important point is you try to please recollect the graph, volume charge distribution graph. Please try to recollect that. Right. If I am plotting a graph taking a G along y-axis or along x-axis, you are very clear it's a straight line till this point. Thereafter, it behaves like a curve because it is inversely proportional to R square. And here it is directly proportional to R. But you should see one observation here. What is that observation? You can see that there exist 2 points, a particular depth, a particular altitude, where the magnitudes of G are same. I repeat, you will find 2 such points, one at a depth D, 2 at a height h, where the acceleration due to gravity is the same. Not only one, you will have a lot of such points. You will have a lot of such points. So for example, what is GH? Just now we have written GH is G naught R by R plus H whole square. And the G depth is G naught 1 minus T by R. So what you will do is you will equate both. By equating both, what you will get? R by R plus H whole square becomes equal to 1 minus D by R. So all such H and D that satisfies this condition the acceleration due to gravity will be this same at that depth, at that height. Any doubts, boys and girls? Are we clear? Now, so G variation with the depth, G variation with the height, we have gone through. Now there is another factor, rotation factor. Because all this, when I am doing, I am taking Earth as a inertial frame. And I have taken a poles actually. What about the point is somewhere else? So in that case, you will consider that effect as a rotation effect. And that effect is actually called as a latitude effect. Variation of Z, variation of Z with latitude. Okay. Now, how to study this particular concept? Boys, this is your ear. Fine. And this is the axis about which our earth rotates. Fine. Fine. Now, I wish to select a point over here. I wish to select a point over here. Here. Exactly. Remember, this is called equatorial plane. Equatorial plane. Are you are seeing a 2D diagram. Actually, it's 3D. So in that case, it will become a plane. With this plane, it makes an angle theta. Correction, standard representation phi. Now, who am I? An observer attached to the reference frame of the Earth. When I am observing this particular object on the surface of the Earth at that latitude position, I will see that this will experience two forces. One is the natural mg naught. The other force is at this point, if the radius is r, mr omega square, mr omega square. So therefore, observing these points, the net downward pull mg phi can be considered as mg naught minus your components. This is also 5 mr omega square cos phi. Please tell me till this point, do you have any doubt? This is the net pull toward the center of the earth as observed by a frame attached to the earth. Till this point, any doubt? Boys and girls? But what is R? R here, if you see the geometry over here, if you see the geometry over here, this is R. This is capital R. And this is a phi. Agreed? Arya, don't compromise. Agreed or not? So what you can write R? R is nothing but R cos phi. Right. Let this be equation 1 and let this be equation 2. 1 and 2 implies G phi is G naught minus R omega square cos square phi. So this is the expression for G as a function of phi. Now you can see clearly yet poles phi is equal to 90. So in that case, G phi becomes Z0. So no effect of rotation of Earth. No effect of rotation of Earth. But at equator, you don't find latitude effect. Now, at equator, bolo. Now you will have phi is equal to 0. So in that case, G phi is equal to G naught minus R omega square. Maximum effect or least G. So if I am moving from pole towards equator, what is happening? G phi decreases. G phi decreases. So these are the three different factors that could affect the value of G. So till this point, any student having doubt? Yes. Yes, of course. What is radially outwards? This is the radius there. That is the circle there. That's what I have written. Away from the axis. Right. Next. Here, if someone asks me G phi minus G naught by G naught. So someone asks me, this is called fractional change in the value of G. This will become R omega square by G naught. Nearly for our omega, taking that radius factor, omega factor, G factor, all that into consideration, this will become 1 by 291. Don't forget, omega is 2 pi by 24 into 60 into 60. R is 6,400 kilometers. You substitute all, you will get this result, 1 by 290. Not only that, if the earth speeds, if the angular velocity is increasing, at a particular point, G phi becomes 0. A person on the equator feels weightlessness. Okay? This is variation of G. One with respect to height, two with respect to depth, and the other rotation. Till this point, any doubt? Every student in the class. Right. So now the next topic is that gravitational potential energy. Gravitational potential energy. That is my next concept. Right. Now, you already studied in electrostatics also. What is that you studied in electrostatics? What is that you studied in electrostatics? This is the surface. Okay. An object on the surface, say at this point, let this be A. And again, this point, let this be B. So, potential energy, electrostatics, potential times charge. Whereas in gravitation, you will write that as minus G capital M by R times the mass of the particle. For a point mass, This is how we define the gravity. This is called gravitational potential energy. It will be negative because attracting. Now, for example, this is R and this is small r. Then in that case, at A you will write like this. At B you will write this as minus G capital M small m by R. So as you move up, denominator increases, fraction decreases, negative term decreases. So potential energy increases. Don't feel that potential energy decreases. It is a negative term. Got the point? As you move up, as you go height, more and more height, what is happening? Potential energy is decrease, magnitude decreases, but it's a negative term. So potential energy increase. Very simple. You need to do work against Earth's gravitational force to move it from A to B. You are doing work. That work is stored in that object as a form of potential, and that is called gravitational potential energy. Fine. Now my question is very clear. Good. The same observation. Now you will consider this as Earth of radius capital R. Now I am projecting an object here with a velocity u. Now what will happen is that it will reach some height and comes to instantaneous rest. And let this height be h. Now, please try to understand. We will label this as two locations, A and B. Now, here energy must be. So, what is the total energy? Earth plus mass system must be conserved. You have projected. That's all. I am conserving from thereafter. Lot of students will question me. You have projected. You have done some work. No, I am not conserving from that point onwards. Where I am starting up with? I am starting up with the moment when I have released the object. The total energy is conserved. So therefore, total energy at A must be same as the total energy at B. So when I am writing it like this, my point is very clear. I am focusing purely on totally on non-dissipating forces. There is no air. Air do not offer any viscous drag. All the forces are conservative. They are all matlab only one force, gravitation. Now the question is at A, what are kinetic energy plus potential energy? R plus H. That's the relation. You know? So now you need to solve this. How to solve this? U square minus 2G capital M by R is minus 2G capital M by R plus H. Okay? By solving, you will get a relation between. By the way, wherever you have Gm by R square, you can write it as G also. Remember, when I am writing G, it's on the surface at pole. So this is equation 1 and this is equation 2. Using both these two equations, you can say that H is u square by 2g minus u square by r from these two equations. And remember, this is the expression for maximum height attained. Maximum height attained. And don't use formula u square by 2g. When I am using u square by 2g in kinematics, my point is h is very, 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 very small when compared to capital R. RR, radius of the earth is of the order of 6,400 kilometers. Whereas the heights which you are discussing is not even 1 kilometer. So in that case, variation of G is neglected. G is almost constant. So in that case, we will use H as u square by 2G. Even the term MGH which you are using is due to the same reason. The only potential difference is MGH. Actually, it is not potential, it is potential difference. But from gravitation chapter onwards, you should not ignore that. So this is the expression for maximum height. And this is the potential energy concept. Now tell me, you have any doubt on this? Boys and girls, if you have any doubt on this, now I have one more concept to discuss, and that concept is object moving along the tunnel. Object moving along the tunnel. In this case, this we can consider as earth. This is a tunnel dug along the diameter of earth. So imagine earth is uniform. When I am dealing this, earth is considered to be uniform. Density is throughout the same. Practically, that is not correct. Now you have released an object over here. You just released an object over here. Now try to please understand when it reaches at a particular distance, say R, this will experience G. So that G is, since it is attractive, I am representing it by minus 4 by 3 pi G rho R. Remember, acceleration is proportional to displacement. Then what is this condition called? Yes, this is the condition for SH1. SH1. So therefore, this you can represent as minus omega square R, and the omega term represents 4 by 3 pi G rho. Okay, and therefore time period is 2 pi by omega. Right. And now, rho is nothing but mass by volume. 4 by 3 pi r cube. Now, 4 by 3 pi r rho can be represented as m by r square. So, therefore, time period is 2 pi by, this year only you can do that correction. 4 by 3 pi r rho g can be written as G capital M by R square. अरे यार correct है ना? GM by 4 pi 3 pi R cube actually. 4 by 3 pi G रोएगा निकाल से. So therefore time period is nothing but GM by R cube. This is the first case. This will obviously execute as such. Remember, you have released it from rest. You have released it from rest. It will come to rest to the left extreme. And it keeps on working to and from motion. Right. Any doubt till this point? Paka? Sure. Next. What if the tunnel is not dug in the way that I have described just now? That is the tunnel. And you have the center of the earth over here. And remember, this is your radius capital R. Now you have released it. Now it has reached some point over here. Remember, this is some point which is at a distance x. As per my condition, this is some r. And let this makes an angle theta at that instant. Remember, this point will experience acceleration due to gravity towards the center of the earth, which can be given as g is equal to, right, just now I taught 4 pi 3 pi g rho r. Now, right. Now, the component we will take, yes, this as x-axis and this as y-axis forever. And the component that drives along x is mgx, which means mg, if this is a theta, this will be 90 minus theta. So mg sin theta. So 4 by 3 pi g m rho r sin theta. And remember, this is attractive still, directed towards this point. Why I have given minus sign? Because it is directed towards the center. Right. So therefore, fx is finally minus 4 by 3 pi g m rho. Can someone explain what is r sin theta? X. From the triangle, you can see that. If this is r, this is theta, this is r sin theta, which you will call it as x. The force is directly proportional to displacement. What condition this will come under? SHM. Force constant is this. So therefore, in this omega term is once again 4 by 3 pi g rho, same as above. So even now, the time period is 2 pi by omega, which is nothing but 2 pi by root g capital M by r cube. Whether you dug along the, what do you call, the center, when the diametrically tunnel taken or carved wise tunnel taken, the time period of oscillation is still the same. Remember, all these correct conditions are true only when it is released from rest. The time period remains the same. This is one big observation you need to have. Any doubt till this point? Any doubt? Are we clear? Right. Next. Orbital velocity of a satellite. Orbital velocity of a satellite. Remember, this is Earth. Here is your center. Now I want an object to move along Earth in a circular path. Remember, what is a basic trouble that I will face? Tell me, anyone in this class. Gravitational pull exists. Now here you have an object here. This object will experience gravitational pull. That object will experience a gravitational pull. Fg. Okay, fine. And this object is moving along the circle at that instant with a velocity v0, which is called orbital velocity. Now, what is the condition that should satisfy for the orbit to be circular? For the orbit to be circular, the necessary centripetal force must be supplied by gravitational force itself. If the gravitational force supplies the necessary centripetal force, pass. That's all. It will move in circular orbit, which means mv0 square by r is g capital M small m by r square. So which means v0 is under root gm by r. This is the formula for orbital velocity. I should say orbital speed actually. Remember, this is independent of mass of satellite, mass, size, shape, all factors. Suppose if R is tending to capital R, this is called close to Earth satellite. Close to Earth satellite. In that case, V0 will become root G capital M by R. This you can write it as root RG also. Remember, this value is nearly, it is of the order of some 7.6 kilometer per hour. Now, one point, just tell me, as you go up, as you move away from the center, what happens to the orbital velocity? Will this increase or decrease? As you move away from the center, it will decrease. So therefore, related to orbital velocity, my point is very clear. As you move away, keep moving away, radius keeps decreasing. What about time period? Time radius, as radius keeps increasing, speed keeps decreasing. What is the time period? 2 pi r by v naught. So you will get this as 2 pi root r cube by g capital M. This is the expression for time period of revolution. So you can confirm this as t square proportional to r cube. T square proportional to r cube. Okay. So if it is a close to Earth satellite, r tends to r, t becomes 2 pi root r cube by g capital M. This is nothing but 2 pi root r by g. Nearly some 83 minutes odd. Nearly some 83 minutes. Somewhere around that area you will get. Okay? So please try to understand orbital velocity is what I have given you right now. 2 pi root r by g naught. 83 minutes roughly. Okay, it means at this rate it will maximum cover 17 times. In a day, this will make 17 revolutions in a day. Got the point? Any doubt till this point? Right. Suppose if T becomes 24 hours and a satellite orbit is in equatorial plane. Equatorial plane. Such a satellite is called geostationary satellite. Such a satellite is called geostationary satellite. So nearly for that satellite, the height is also very high. If it is a geostationary satellite, it is of almost very high values. If I am not mistaken, that will be around some 36,000 kilometers high. Geostationary satellite will be, that is also called parking satellite. So geostationary satellite will be at a height of nearly what do you call around 36,000. What is the radius? What is the expression for the time period of what is the expression for, I don't know, what is the value of the radius of close to Earth satellite? 6,400 kilometers. Whereas this satellite will be at a height of how much? Nearly 36,000 kilometers. So it will be at a height of 36,000 odd kilometers. So its speed is nearly around, the speed is nearly around 3 kilometer per hour. Nearly. I'm not giving you the exact values. Nearly around 3 kilometer per hour. This is also called as geostationary. Sometimes this is also called as geosynchronous. Geosynchronous, or this is also called as parking. Actually means they have removed this from the syllabus. Parking, or this is also called as a relay, or this is also called as a transmitting satellite. Why? Because the live cricket matches all are delivered only due to this satellite. Always in front of us. Always in front of us. But when I will say that it is a geostationary satellite, its orbit must be in the equatorial plane. And the sense of rotation, so orbit is in equatorial plane. sense of rotation of Earth and sense of rotation of satellite must be same. That must be the same. So how if the Earth rotates from west to east? So geostationary satellite also will rotate from west to east. That's all. So this is about geostationary satellite. Now the issue is this is all fine. It's a very simple theory, orbital velocity, and one more important point. In a circular, if a satellite is in a circular orbit, okay, Earth. Earth, right. Now this is at a distance r. Now what is the total energy here? Kinetic energy plus potential energy of mv orbit square plus minus g capital M small m by r. Any doubts? Now V naught, you already know what is V naught, root G capital M by small r. This you will get as G capital M small m by 2 small r minus G capital M small m by r. This will become minus G capital M small m by 2r. For circular orbit, please note that total energy is to kinetic energy is to potential energy will bear the ratio minus 1 is to 1 is to minus 2. So as you move away, total energy increases actually. Any doubt? Right. All that which I have discussed right now is related to circular orbit. Right. But practically speaking, most of the occasions, the real satellites are close to circular orbits, but they have some uh, ellipse also. Like, for example, you take a situation like this. This is Earth. Right. This is your Earth. Now I have an object over here. I just dropped that. If I drop that, it will follow a straight line path. It will simply follow a straight line path. I have projected, but not with orbital velocity. I have projected it a velocity lesser than orbital velocity. In that case, it follows an elliptical path. Right. So remember, this is the second situation. Okay. It follows an ellipse path. Please notice that. Now I have projected with perfect orbital velocity. Then it follows a circular path. We will name the paths so that there is no confusion. 1, 2, 3. And I am projected with slightly more than orbital velocity. Less than orbital velocity, ellipse striking Earth. More than ellipse. No, no, more than orbital velocity. Slightly more than orbital velocity. Again, it will follow right is following an ellipse again. 4. Now I have projected with a velocity called escape velocity, which I will discuss now. It will never return back to Earth. So in that case, the path will become parabolic. So it won't return back to Earth. Please remember, in case of one dropped, in case of two, the velocity is less than orbital velocity. In case of 3, exactly orbital velocity. Right. In case of 4, more than orbital velocity, less than escape velocity. In case of 5, equal to escape velocity. So, in case of dropping, it followed what path? Straight line path. Straight line. In this case, ellipse. In this case, circular. In this case, ellipse again. In this case, parabolic. Those are the three different paths that will be taken care by that object. Now we will focus on the escape velocity. What exactly is the escape velocity? So I have clearly given a detailed information about see, any satellite which is either moving in ellipse or circle, it is called bound. Total energy will be negative for that. Bound satellite. Now, what is happening for you is in such cases, like for example, as I mentioned, in close to Earth satellite, this is nearly 84.6 minutes, slightly 1.4 hours. Right. So please try to understand in such cases what will happen, the Earth, it is bound to Earth. It is moving there and there only. Whereas the case which I am discussing right now comes under escape velocity. So what is escape velocity? Escape velocity. Now here is your planet. This is called planet Earth. Radius R. And I have an object. I want to project with some velocity UE so that it will never return back. What is the formula for maximum height? Just try to remember U square by 2G minus. When U becomes UE, H tends to infinite. Yes or no? I repeat, in that formula, if you project with a velocity such that H becomes infinity, never return back to Earth. వాడికి నిద్ర వస్తుంది చూడండి అందుకే చదివే 10 మందిని పంపించమంట క్లాస్ పంపించారు U is equal to UE. H tends to infinite. In this case, if H is tending to infinite, it is possible only when UE square is 2RG. and UE is root 2 RG. Remember, when you project at this speed, total energy is just equal to 0. This velocity is called escape velocity, and this is nearly 11.2 kilometer per hour. There is a special terminology, cosmic velocities. First cosmic velocity ante orbital velocity ki తీసుకుంటాం. Next cosmic velocity ante it is like 11.2 escape from the earth. Third cosmic ante escape from solar system. And there is a terminology. I don't know how practically people are using this, but in fact that is a fact, right? So escape velocity, it is independent of what? You just see. Did you notice any relation? Now I am projecting with such a speed where it should never return back. So escape speed does not depend on mass of the body projected. From surface of the earth. Also, it is independent of angle of projection. Total energy 0 is what you want. Total energy 0 is the condition, independent of angle of projection. Remember, this is the case where you have projected it from the surface of the earth. Suppose you have your planet is this. This is the orbit. Right now it is orbiting with the VO. See, as long as its speed is V0, it move in circular. Due to some rocket fire, if this speed suddenly increased from V0 to VE, what happens? V0 is root G capital M by small r. You know. You want total energy to become 0 at this point. Minus G capital M small m by r plus half m VE square is 0. So VE is 2G capital M by R. This is nothing but root 2 times orbital velocity. So if you are already in a circular path, you are orbiting around Earth with some velocity V0 called orbital velocity. Suddenly, if your velocity increases by root 2 times the previous value, you will escape. So what is that percentage change? Root 2 minus 1 by 1. So 0.41, 41% nearly. If you increase the speed suddenly by 41%, what happens? You will escape from the particular orbit. So these are basic theory contents. Now we will start doing problems. A basic theory I have done. Kepler's laws is also there, which I will discuss undoubtedly. Right. We will now start doing problems one after the other. Right. Now we will start. We will start basic models first. Please note this question for a while. I require some time for my pencil to be charged. Find the height at which the gravitational field of the earth becomes 1/4 the field at the surface. Find the height at which the gravitational field of the earth becomes 1/4 the field at the surface. GH is 1/4 G naught. G naught times R by R plus H whole square is 1/4 Z naught. So with this, you can write 2R is R plus H. So H is R. At a height equal to radius of the earth, acceleration due to gravity is 1/4 of what was that on the surface. Right. Next. Now try this question. Assuming Earth to be a sphere of uniform mass density, how much would a body weigh halfway down the center of the Earth if it is weighed 100 newtons on the surface? Common sense question. You already know G at a depth is G naught minus into 1 minus D by R. Halfway down until D is equal to R by 2. So ZD becomes G naught by 2. So therefore weight will become 100 by 2, 50 Newton. Is weight becoming 50? What about mass? Mass still remains the same. What is happening to that? Mass is the same. Because of the pull change, gravitational pull difference, you are finding a lesser weight. Almost at the center of the earth, practically zero. Right. So I'm just raising up the level of difficulty. Now try this. A planet of radius r equal to 1/10 the radius of the earth has the same mass density as earth. Scientists dig a well of depth r by 2 on it and lower a wire of the same length and of linear mass density 10 power minus 3 kg per meter into it. If the wire is not touching anywhere, calculate the force applied at the top of the wire by a person holding it in that particular place. Radius of the earth is asking to be taken as 6 into 10 power 6. Acceleration due to gravity on the earth can be taken as 10 meter per second square. First, see, try to please understand what tenth the radius of the earth has the same mass density as the earth. Now, see, please try to understand the question carefully. And this is the planet. So here is where you have dug. Of course, for my understanding, I am drawing a bigger diagram, R by 5. Now here is the root. Here is the root. Here is the rho. Now, please try to understand. You take a small element over here, a very small element. You draw the free body diagram of that small element. Here the tension is T plus dt, and it will have weight also, no? T plus, please help me in writing the weight of that element. The mass of that element, let this be dr, which is at a distance r. Okay. So what is going to be the weight of this element? Weight of this element. So it will have weight dmg at that point. So g at that point is nothing but 4 by 3 pi rho g r. And dm is nothing but mass per unit length into dr. So dt is nothing but t plus dt up, but t plus mb down. So dt is nothing but dm times g. dt is nothing but lambda dr 4 by 3 pi rho g r. Till this point, any doubt? Pakka? Right. So dt is 4 by 3 pi rho g lambda r dr. Now you do integration. Can I ask you one point? As you go down, tension becomes zero. You are moving in the decreasing direction of r. So therefore, you should not leave it like this. You should leave it with a minus. Can you please tell me why I have taken a minus sign? Because as you are decreasing r, tension is also decreasing. So therefore, now in this case, after doing proper integration, 4 by 3 pi rho g lambda, अरे भैया ये 1 by 2 r square minus r square by 5 కదా integration. अरे यार this is r. What about this point? Wrong. 4r by 5. So therefore, I told you lot of times, don't do by yourself. You do while it is in a practice session. But whereas in my presence, better you hear. Now what is going to happen in this 16 by 25 r square? So that is the difference of the tension. So T is 4 by 3 pi rho g lambda. अरे बात ये 4 को 2. And it will become 9 by 25 r square. I am not dealing anything with planet, etc. like kind of thing. Later I will go with. Right. So this is nothing but 2 by 3 pi rho g. Okay. R 1 r I am taking. Okay. Next balance lambda r by 25 times r. 9 is also there. Okay. 9r. If you permit me, I will do small modifications. Wherever lambda r by 5 is there, that comes under mass. Right? You said this is a 10 power minus 3 and a radius 1/10 of the radius of the earth. 6 into 10 to the power of. No, my point is, hold on. Why should I change? Okay, why? Because r is the radius of the planet. But they did not given the radius of the planet in the question. They have given the radius of the Earth. And he mentioned what you got, 1/10. 1/10. So therefore, 6 into 10 to the power of 5 by 5. You can write this as 1 minute. 60 చేయొచ్చు కదా దీన్ని. 12 లేకపోతే 100 వస్తుంది ఇంకా 10 మిగులుతుంది 120 kg. Right. Next, hold on. Next is, if you permit me, 4 by 3 pi rho g r is for this planet. Is for this planet. Kada? And for this planet, it will become g earth by 5 because density is the same. So g earth already given as 10. So this will become how much? 2. Right. Now you try to substitute everything. So, no issues. 2 by 3 pi rho g r, right? That I will write it as, if it is 4 by 3 pi rho g r, it is a 2. If it is a 2 by 3 pi rho g r, it is 1. 1 into lambda r by 5 can be written as 120 into hold on, don't get aggressive. Into 9 by 5. Anything else left? 1 minute. Don't get confused. You don't require this R here. 9. So that's the deal. By properly doing, you will get the answer. Don't get any confusion. Got the point? So I have done this very carefully, each and every step. Proper integration step is required there. Already I have taken 1/5. There is another 2 by 3 pi rho g r is the planet acceleration due to gravity, which is equal to 1/5 the acceleration due to gravity of Earth. Right. So likewise, you need to substitute. Right. Hold on. So this is how you need to do problems of this type. Till this point, do you have any doubt? Clear? Right. Next question. Suppose the Earth increases its speed of rotation, at what new time period will the weight of a body on the equator becomes 0? Take g is equal to 10 meter per second square and radius of the Earth r is equal to 6,400 kilometers. Can you please express what exactly he wants? What omega is required so that G0 na G50? G can't be 0. So G5 is G0 minus R omega square at a equator. So what is that you want is G5 is equal to 0. So omega is G0 by R under root. Time period. Time period is 2 pi root R by G0. This is nearly 1.4 hour. Right now, what is the time period? Presently, 24 hours. In that case, G5 is not equal to 0. If T becomes 1.4 hour, G5 becomes 0. Objects on the surface of the earth becomes object on the surface of the earth feels weightlessness. Mass 0 కాదు. So objects on equator feels weightlessness. Right. Next. Next question. This one is a very famous model. Start doing this. In this question, what they exactly want? Calculate the time period of the satellite on the equatorial orbit at 1 point. They have given you radius. Fine. So remember, there is a confusion here. Have they given radius? Or they given you height of the orbit? So therefore, radius is r plus h, which means 6.4 into 10 power 6 plus 1.4 into 10 power 6. This will become 7.8 into 10 power 6 meters. Right. Here we already know time period is 2 pi under root r cube by g capital M. Here M stands for mass of the earth. So now you substitute in this particular data 2 into pi into under root r cube 7.8 cube into 10 to the power of 18 divided by g 6.67 into 10 to the power of minus 7. Sometimes what you can do is, I'll just give you a technique. When you see gm, you can write it as r square g also. It's a rough technique. That is fine. Otherwise, this is what you have. Mass of the earth given? No. Which means he wants us to use the same relation. Which means, what is that? R square 6.4 into 10 to the power of 6 whole square into 10. By solving which you will get the answer. You will get around the time period term. You will get it around some 6831 seconds. It is not a bigger height actually, lesser than the radius of the earth. So not close to the earth, but fine, nearer to the earth. What is the speed of the satellite in this orbit? Very simple. V is equal to root RG. Or okay, if you are not convinced, gm by r. Again, my suggestion is r square g by small r. Okay. So by substituting, you will get the values around 7174 meter per second. I'm just giving you an idea how to do. My intention is not to use a calculator and substitute all these things. Next, 2 points are very easy. The third point is a touching. This is where I should give more time. If the satellite is traveling at the same sense as the rotation of the earth, west to east, what is the time interval between two successive times at which it will appear vertically overhead to an observer at a fixed point on the equator? So what is that you need to find relative angular velocity first. What is relative angular velocity? So obviously omega, see, time period of earth is high when compared to the time period of the planet, satellite. Reverse. Omega earth will be relatively slower when compared to the omega satellite. Omega satellite minus omega earth. So relative angular velocity is what you need to take. Fine. So if I am stationary, I see that relative angular velocity is so and so. That is the angular velocity. The time period T is 2 pi by omega relative. So which means 2 pi by 2 pi by satellite, time period of satellite, minus 2 pi by time period of rotation of the earth. Finally, T is TE, TS by TE minus TS. So by substituting, you have already that data, no? This is T satellite, and you know T Earth is 24 hours. Right. By substituting properly, you will get the answer around some 7417 seconds. See, gravitation related, first we should have some final answer. Otherwise, it will kill. My focus must be teaching you the concept, not how to use the calculator in this. Right. So very, 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 very important model. And first of its kind. Till now, this is the best problem as per my point. Next question. That's the question. A satellite is revolving around the Earth in a circular orbit in a plane containing Earth's axis of rotation. Angular speed of the satellite is equal to that of the Earth. Find the time it takes to move from a point above the North Pole to a point above the equator. Have you understood the question? Which means you assume this situation here. So from here to here, which I can write as 1/4 the time period. 1/4 the time period. That's it. 6 hours. So this time is 1/4 the time period of rotation of the earth. 24 by 4. 6 hours. అరే నువ్వు ఫస్ట్ చెప్పావా 6 hours అని? ఇప్పుడు నేనేమంటానంటే కరెక్టే, ఎగ్జామ్లో కూడా చేస్తే అది బాగుంటుంది కదా. ఇప్పుడు ఇక్కడ చెప్పి ఉపయోగం ఏముంది, వాడికి చెప్పి ఉపయోగం ఏముంది, నువ్వు ఆలోచించు ఒకసారి. మీరు చిన్నవి అంటే అదేంటి చిన్న చిన్న స్విమ్మింగ్ పూల్స్లో మీరు ఈదేసి నేను సప్త సముద్రాలు ఈదేసానని ఫీల్ అవ్వకూడదు. నేను ఐ ఎంకరేజ్ దట్. అది ఎగ్జామ్లో కూడా ఎందుకు రిఫ్లెక్ట్ అవటంలో ఆలోచించండి. రైట్. క్వశ్చన్ పేస్ట్ చేసినంతసేపు పట్ల ఆన్సర్. రైట్. నెక్స్ట్. One more question. I am just raising up the level of difficulty. Raising up the level of difficulty. So please track carefully. Just raising up the level of difficulty. It is an H.C. Verma question actually. So that the scale reading will be very close to so and so. And if I have a doubt, I'll paste that part also. So that the scale reading will be very close to omega naught into 1 plus or minus 2v omega by g. See, I am assuming ship is not sailing at all. Just ship is on the equator. Right. Now, what is the weight in that case? Means it is just at the equator with this one being rotating at omega speed. In that case, W1 is mg minus m omega square r. Any doubt in this part? Right. Suppose if the speed is rotating, I say the speed is sailing, actually rotating undoubtedly, but with respect to Earth, it is sailing. It might have some speed. See, remember, with respect to the axis of rotation, two possibilities are there. This is when ship is at rest. If ship is sailing, two possibilities are there. One possibility, V plus R omega. The other possibility, V minus R omega. Depends on the sense of, suppose if it is moving along west to east, you will write V plus R omega, right? Suppose if it is in other case, you will write V minus R omega. So in this case, what will happen to W? Mg minus, in that case, omega is different. You should take relative omega. So what is relative omega? Relative omega is V plus R minus R omega by R. This is, yes or no? That's what you need to mb square by R. So now I consider relative. See, if it is V speed, mv square by R. But V, no idea, no? Whether it is, both possibilities we should take. Now W is equal to mg minus m by R V square plus R square omega square plus or minus 2VR omega. So therefore, this you can write as W is mg minus mr omega square minus mv square by R plus or minus 2mv omega. 2mv omega. Yes or no? Now, this you already know, W1 minus mv square by r plus or minus 2mv omega. Right. What do you want? Show that the scale reading will be very close to. Now, I think m term must be replaced here. W1 minus m times v square by r plus r minus 2v omega. By the way, from the first part, I can say that m is nothing but w1 by g minus r omega square, right? So if I substitute that here, w1 minus w1 by g minus r omega square times v square by r plus r minus 2v omega. Right. So by almost by proper adjustment, w is w1 times 1 minus 1 by g minus r omega square into v square by r plus r minus 2v omega. Now you go for binomial expansion as best as you can. Because r omega square by g is very, very small when compared to g. This you can write as 1 by g minus r omega square can be written as 1 by g times 1 plus r omega square by g. Agreed? So therefore, 1 minus 1 by g times 1 plus r omega square by g into v square by r plus or minus 2v omega. Okay? By solving all, finally, you will get, is that right? Every part, 1 by g I have taken common, right? 1 by g I have taken common, and this will become 1 minus r omega square, 1 plus r omega square. Right. Clear or not? Just please confirm. అరే జీ కామన్ తీస్తే 1 by g అవుతుంది అక్కడ 1 minus r omega square by g, you'll write it as 1 plus r omega square by g. Right. So you need to do some multiplication part here. So you will get v square by rg. Array, don't get confused. Product of these two. And again, product of v square r omega square by rg square. Product of these two. Next, product of plus or minus v omega by g. Plus or minus 2v omega r omega square by g square. These are the terms finally left for you. So in these terms, these terms are very, 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 very small. But prove the term is small. So therefore, W is nearly W1 times 1 minus 2v omega by g. Plus or minus, correct. Any doubt?